Okay, let's get started. Thank you for braving the ice and snow this morning. I mentioned on Tuesday that assignment 9 was due today on Thursday. Obviously, I misspoke. Assignment 9 is due, as usual, next Monday at 11:59 p.m. Any questions about assignment 9? All good? Okay, so let's carry on. We're working our way through a section on open challenges or open questions in evolutionary robotics. We finished last time talking about modularity. There were a couple of slides that we didn't get to in lecture 13. We're a little bit behind where I'd like to be at this point in the semester, so we're just going to skip over those slides for now. We're going to start in fresh on lecture 14 today. So we were discussing in lecture 13 this issue about modularity. If you want, as an organism or as a machine, to solve some complex problem, you have to decide how to break that problem down into simpler parts. Last time we looked at two different approaches. Either the roboticists decide for the robot how to break the task down into simpler pieces, or we create an artificial neural network that allows evolution to decide how to break the problem down into simpler pieces. So we looked at a special kind of neural network last time where, depending on the robot's current sensory perception, it could use different parts of the neural network to drive the motors, right? And evolution could decide what sensor values triggered which parts of the neural network, and by evolving the weights of those different modules in the neural network, evolution could determine what the robot did when those different modules were in control of the motors. Right? Okay. We're going to switch to a different problem today. The answer to that problem, or at least a partial answer to that problem, is an algorithm called the NEAT algorithm, which was followed in the literature a couple of years later by the hyper-NEAT algorithm. You can read, the assigned reading for today is about NEAT. The optional reading is about hyper-NEAT. So the problem that these two algorithms were designed to solve is the competing conventions problem, which I actually mentioned on Tuesday when we talked about the genetic algorithm. In the genetic algorithm you're implementing for assignment 9, there is only mutation, but there is not sexual recombination. Why is recombination not in assignment 9? What's the challenge about getting evolution to recombine genetic material from two different neural networks?
Usually doesn't work very well.
It doesn't work very well, right? If I cut your PC and your Mac in half and I put the two halves together, what's the probability that I'm going to get a new laptop that works better than either original machine? Not very likely. Turns out it's the same case with neural networks. If we evolve a population of robots, and in that population we have two different robots, they have two slightly different neural networks. They're running on different operating systems, so to speak. If we take those two neural networks, cut them in half, and combine them, probably not going to work. But recombining genetic material from different individuals, yep?
Is there any possibility that the combination will produce better result?
Is there any probability?
Yes.
Yes, there is some probability, but it's pretty close to zero. There is a probability that if I cut your laptop in just the right way, I might actually get a machine that's better, but the probability of that happening is exceedingly low, right? So what NEAT was designed to do is actually increase the probability that when we do cut two neural networks and glue the two halves together, that in some cases we get a neural network that's better than either. The probability is still low, but it still happens from time to time. Right? Okay, but sexual recombination is useful. Mother Nature invented sex for a good reason, which is often, again, if you combine genetic material from two organisms, you often bring together the best of both worlds, right? There might have been an innovation or a mutation in one lineage and in another. These two species or these two organisms are able to do slightly different things. They've solved different parts of one bigger problem, coming back to this issue of modularity, perhaps by recombining it we can bring together these two innovations that have been found in two different lineages and combine them in the same organism, or in our case, when we finish lecture 14 today, as you'll see, in the same robot. Okay, so let's have a look at this competing conventions problem in a little more detail. So here's a little cartoon to show the problem. And you'll remember that when we were talking about artificial neural networks, we looked at a neural network that solves the OR problem, then we looked at a neural network that solves the AND problem, then we looked at a neural network that solved the XOR problem, the exclusive OR problem. But I showed you that in order to create a neural network to solve the XOR problem, we have to introduce hidden neurons, right? We need to have these neurons in between the input and the output. And those those hidden neurons have to compute partial results, right? We're trying to perform some complex computation in transforming the inputs into the outputs. In the XOR function, in the XOR network, that was the XOR function. What were the two subproblems that the XOR network had to solve?
Did it just do an OR and then an AND?
Right, exactly. So one hidden neuron solves the XOR problem. The other hidden neuron solves the, AND and OR. And then they combine their result together at the output to compute the XOR function, right? For a lot of problems to which neural networks are applied, the neural networks have to do the same thing. They have to figure out synaptic weights to compute some complex function, and in order to do it, they're going to have to compute partial results, right? Let's imagine now, forget AND and OR, let's imagine that we have some problem, and in order to solve this problem successfully, the neural network is going to have to compute three subproblems, A, B, and C. Let's imagine that this network is using hidden neuron 1 to solve subproblem A, neuron 2 to solve B, and neuron 3 to solve C. Let's imagine it's not perfect. It's doing a pretty good job of A, B, and C, but it's not perfect. Imagine these two neural networks are in a population of evolving neural networks. In this population, there is another neural network that is also doing pretty well. It's also almost figured out how to solve A using neuron 3. Hidden neuron 2 is almost solving B, and hidden neuron 1 is almost solving C. Right? So far, so good. We've got two networks in the population that are doing pretty well. Let's imagine further that this network is doing really well at A and B, but not that great at C. This one is doing not that well in A and B, but has nailed C, really knows how to do C. What would we like to have happen here?
Have it just be machine 1's A and B and machine 2's C?
Absolutely, right? We would like to try and cut these two networks in some way and bring those two pieces together so that we combine the A and B from network 1 with the C from network 2. That's what we would like to have happen, right? Remember that we don't know this is going on, right? We're just defining we're trying to create some recombination operator that from time to time will pick two individuals in the population, pick some way to cut them, and then combine them. If the combined network does better, then it'll survive. If it doesn't, then it's thrown away.
I just wonder, how can you determine, like what you have just said, that A and B would much better than the other one?
How would you determine it?
Yeah.
All right, so we're assuming we don't know, but imagine that, let's say we were evolving a population of neural networks to solve the XOR problem, right? And unbeknownst to us, there are two networks in that population. One which is getting really good at solving AND, using one of its hidden neurons. And the second network is getting really good at solving OR with another one of its hidden neurons, right? We don't know that, but if there is something that was to combine those two networks together, we might obtain a new network that is solving XOR, which is what we want it to do. Make sense? Okay. All right. So here we go. How do we cut these two networks to combine A and B? Okay, silence is good because actually there is no way. Maybe if we went in and sort of cut like this, right, maybe we could do it. But if we're assuming we're just kind of slicing through the network somehow, there's no good way to do it, right? So that's what this little cartoon down here shows. We could, for example, cut through here in both of them. And if we cut through here, if we cut between neurons, hidden neurons 2 and 3, then the first child ends up with A and B from parent 1 and A from parent 2. And the second child ends up with C from parent 2 and B and C from parent 1, right, for example. That's no good because this one did not inherit C at all, and this one has no A, so both of the two child networks are missing an important piece. If we cut through here, for example, instead, how does that do? Same problem, right? There is no good way to cut through these two networks to bring together what we really want, which is A and B from here and C from here. The reason why is because these two networks have competing conventions, right? Remember back to the XOR network, it doesn't matter whether a network computes OR using neuron 1 and using neuron 2, or vice versa, right? It doesn't matter as long as one of the hidden neurons is computing one of the necessary subfunctions. So they're both doing fine, but they have competing conventions, much like a PC and a Mac, right? They both sort of have the same functions. There's a central processing unit somewhere inside the machine. There's memory somewhere in the machine. There's a disk drive inside the machine somewhere, but they're at different places, and even within the hard drives, there are also subcomponents that are in different places and do things slightly differently. It's again one of the reasons why you can't cut two laptops and glue them together. They actually are sort of performing all the same subfunctions, but in slightly different places and in slightly different ways, right? The same is true of our DNA. We all have DNA that describes how to build heart and lungs and arteries and so on, but they're all slightly different. There's a slightly different convention in all of our different DNA. It's pretty similar, but also some things are not in the same places in each of us. So if that's true, how does Mother Nature solve this problem? Well, she solves it using a trick that is going to be incorporated into the algorithm we're going to talk about now, which is the NEAT algorithm. The authors were pretty clever in picking NEAT as the acronym for their algorithm. It is admittedly kind of a neat trick, so let's see how this works. NEAT stands for neuroevolution, so we're going to evolve neural networks. That's pretty straightforward. Of augmenting topologies. So what does that mean? What that means is that we're going to consider not just the synaptic weights of a neural network, but we're also going to evolve the topology of the network itself. So topology means the architecture of the neural network. How many neurons, how many synapses, and which neurons are connected to which other neurons. So we're actually going to augment or we're going to allow evolution to augment or change the topology of the network. That's what we're going to start with, and then we're going to see how NEAT implements recombination to deal with the competing conventions problem. In your assignments, your genome is a two-dimensional matrix which stores all of the synaptic weights. In the NEAT algorithm, the genome is made up of two lists, and these lists can grow and shrink over evolutionary time. Evolution can add or remove material from the genome. The first list contains information about the nodes or the neurons. So in this little cartoon here, we've got a network that's made up of 5 nodes or 5 neurons. We've got our nodes up here. We can see this particular topology of this network has 3 sensors down here, 1 hidden node, and 1 output node. The second list is a list of synapses, and every element in this list has information about a single synapse. Right? First element in the list here describes a synapse that connects neuron 1 to neuron 4. That synapse has a weight of 0.7. This synapse is currently enabled, so evolution can also flip some of these synapses from enabled to disabled, so it's turning on or off these synapses. And then there's this innovation number down here, and we'll come back to that innovation number in a moment. That's actually the heart of the NEAT algorithm. Okay. Let's have a look at mutation first before we tackle recombination. We notice up here, for example, that we have this particular network here, and we now have mutation operators that don't just change synaptic weights, but they can also add and remove neurons or add and remove synapses. So this particular neural network is mutated. The mutation operator adds a new node here, which is adding a connection here, and it's adding a new synapse here that connects neuron 3 to neuron 4. When that synapse is added, evolution also picks a random weight for that synapse, and the weights are just not shown here. You'll notice these numbers up here. These are the innovation numbers or the historical markings. These numbers are decided by keeping a global counter, and every time a neuron or synapse is added, like here, assign the value of the counter and then increment this global counter. Okay. So at this point, imagine in this evolutionary run that only 6 synapses have ever been created, so the global counter is at 7. So we're waiting for a 7th one to be added. A 7th one is added, we increment the counter to 8, and evolution continues on. You'll notice, let's carry on here. We can also mutate a neural network by adding a node. So here we've got a list of the 5 nodes or neurons that make up this network. Another mutation operator is called, which randomly adds a node to this network. It's added down here, and I'm not actually showing the list of nodes. This is the list of synapses. When a node is added here in the middle of this synapse, we disable this synapse and add 2 new synapses, one that connects 3 to 6 and another one that connects 6 to 5. We've created 2 new synapses, so we give the global counter value to these new synapses, 8 and then 9. So as evolution is proceeding, we have this population of neural networks. From time to time, neural networks that have higher fitness are selected to produce offspring. In this case, the offspring is just a single mutant from the parent. When the offspring is produced, different kinds of operators can be applied. Some of the operators flip a synapse from being enabled to disabled, or they change a synaptic weight, or they delete a node, or delete a synapse, or add a synapse, or add a node. So now we have a growing list of mutation operators, or kinds of mutations that networks can undergo. Okay, so this is all build up for the main event here, which is crossover. Okay, we've got a population of neural networks, and evolution randomly chooses 2 parents that have relatively high fitness. These 2 parents are going to produce 2 offspring, and just 1 offspring here. We're going to produce just 1 offspring, and that offspring is going to combine genetic material from both networks. How are we going to do this? Here's our blue network and our white network. I'm only going to show you the list for the synapses. Remember that each neural network in NEAT has a list of synapses and a list of nodes. We're going to take the 2 parents, and we're going to line up each synapse in each parent according to its innovation number. So you'll notice that in both parents here, they both have a synapse that has an innovation number of 1 associated with them. What does that tell you? Why do these 2 parents have a synapse that has the same innovation number. Remember, whenever we create a synapse, we assign that global counter value to it and increment that global counter.
They're connecting the same two neurons.
They're connecting the same two synapses.
The same synapse.
How do you know they're the same?
Because the identification number is the same.
Because the innovation number is the same. So these two neural networks themselves must have evolved from some common ancestor. Maybe there was an ancestor that had synapse 1. I'll just say synapse 1 to mean the synapse with the innovation number 1. There was some common ancestor that had synapse 1. That neural network in this evolutionary past here might have produced a mutant, and that mutant inherited synapse 1. That original common ancestor survived long enough to produce a second mutant, which is the brother or sister, if you like, of this first mutant, which also inherits synapse number 1, right? So we now have two individuals in the population that both have a synapse 1. They're descended, that synapse is descended from the same synapse in the common parent.
The number itself is arbitrary as long as it lines up, right?
The number itself is arbitrary. The number just indicates if you find the same innovation number in two individuals, that means that little piece of the neural network, it could be a synapse, as in this case, or it could be a neuron, came from a common parent. Right? So if I were to, again, try and cut your PC and your Mac, if I did it very carefully, if I went inside and found exactly where the CPU is in your Mac, and I went in and found where the CPU is in your PC, I know, as a good computer science, as a good student of computer science history, I know that those two CPUs and those two computers are descendants of one of the original CPUs before Apple and Microsoft ever existed, right? They have certain properties in common. They're still pretty different, so I probably have to go inside of those CPUs and go all the way down to the transistor level. But if I did this tracing very, very carefully, I probably could cut your two laptops in half and glue them together and have a laptop that works, right? You're combining, you're not really caring about the parts themselves, but what those parts do, and you're trying to find similar parts in similar machines or similar parts in similar networks, and you're finding the same part in either one, and you're determining or you're defining similarity based on the fact that they're descended from a common ancestor. In nature, when sexual recombination happens, meiosis is a very complex process, but it's doing something similar. It's trying to line up parts of the genome based on historical precedent, because this is sort of, these genomes, parts of the genomes may be in slightly different places in two different organisms, but they're markers in the DNA saying, this is the part that builds a heart, and in this organism, this is the part that builds, this is the part of the DNA that builds a heart. This is greatly simplified, but this is the basic idea. Meiosis tries to line up similar parts in DNA based on common ancestry. All right, that's the basic intuition behind NEAT. I want to make sure that's clear before we carry on. So far, so good? Okay, so here we go. Let's go back. We have our two parents here. They're trying to produce an offspring. We have found this piece, which has the same innovation number, so we line that up. There's also a synapse number 2 in both parents. Synapse 3 that exists in parent 2, but there is no equivalent in parent 1. So we just leave a gap in parent 1 here. We leave this disjoint gene here. We leave this disjoint gene here with no partner gene in parent 1. We see that there is a synapse 4 in both parents. It's similarly disabled, but it doesn't really matter. Line them up. Here's another disjoint gene, which exists, disjoint synapse, which exists in parent 1, but not in parent 2. 6 exists in both. And then there's some excess genes here at the end. Parent 2 has some additional innovations that don't exist in parent 1. Okay. So we've now sort of lined up all of the pieces of these. This is very different from just going in and cutting a neural network. We're lining up all of the pieces, and now we just visit each of these columns in turn. When we come to a synapse that contains, when we come to a column which contains a synapse from both parents, flip a coin, and the offspring inherits one or the other with equal probability. In this case, you can see it's inheriting the synapse from parent 2. In this case, it inherits synapse 2 from parent 1. Here there is a gap, so we simply just copy the disjoint gene into the child. Same thing here, flip a coin, pick synapse 4 from either parent, and it's inherited into the offspring. And we keep going. We get to the excess genes. Those we just copy into the child. These are innovations. These have higher numbers than 1 through 6, so maybe something has been figured out in parent 2. Parent 2 hasn't had a high enough fitness to survive and produce offspring, so maybe 7 and 8 are useful. Let's throw them into the offspring. If you now read off this genome, you can actually reconstruct the phenotype. Remember, the genotype is always the genetic material that describes the thing that's going to be evaluated for fitness. Here's our thing in this case. What can you tell me about this network, just by looking at this network compared to the parents? Did this work? You're shaking your head no. Why no? It is identical to parent 2? Not quite.
No,
One.
3 and 5.
Yeah. It looks similar to both parents, but is also slightly different, right? Because it's inherited different genetic material from the 2 parents. Now, whether this network is actually going to compute a similar function to either parents, that's very hard to say. Right? We're not going to go into more detail about NEAT, but I can promise you this was published back in 2001, and there are now hundreds of papers that use NEAT. For most problems, it does work. You greatly increase the probability that this neural network will compute a similar function to both parents. If it computes a similar function to both parents, there's a pretty good chance that it might actually compute a function in a better way than either parent. So by introducing crossover using NEAT in this way, if we now run this evolutionary process, we might start with relatively simple neural networks, but over time in the population we start to see networks that have similar but different structure, and often that structure becomes slightly more complicated over time, and these networks become more sophisticated and compute more complex functions, and some of those are the functions we're looking for. Okay. NEAT is not that difficult an algorithm to implement. For those of you that want to try and increase the power of your optimization method, you might consider introducing NEAT. At the moment, you're working basically with a neural network that has a fixed architecture, right? You've got 4 times 8, 32 synaptic weights, and that's it, right? You stick with your architecture and change the synaptic weights. NEAT will allow you to evolve networks that have different topologies. Maybe you're trying to evolve your robot to do something and you're not sure whether it needs hidden nodes or not. Maybe you're not sure whether it needs recurrent synapses or not. If it does need hidden neurons, how many hidden neurons? Hard to decide. If memory is useful and your robot may need recurrent connections, how many recurrent connections should it have? Again, hard to decide. NEAT is a good algorithm that allows evolution to figure that out on its own. Okay, that's NEAT. We're going to switch now and talk about HyperNEAT, which, as the name implies, is going to use NEAT inside, but it's going to do something a little more sophisticated. HyperNEAT is going to evolve neural networks using NEAT, and these neural networks produce regular patterns. So you've been evolving neural networks to produce robot behavior. We're going to evolve, in HyperNEAT, we're going to look at these networks here. These networks are evolved by NEAT, and these neural networks are slightly different from the neural networks you've seen so far. they're similar in the sense that they have input neurons up here, and in this cartoon example here, they have just one output. What is special about these neural networks, which have a long name here, compositional pattern producing networks, or CPPNs, is they take spatial coordinates as input, and the output determines the value at that position. So I'm going to show you an example at the board here, and then we'll come back to the reason for why you would ever want to create a neural network that takes positions as input and paints values or determines values at that position. Let's take a two-dimensional plane for a moment. Let's imagine that this two-dimensional plane has an x-coordinate and a y-coordinate. Let's imagine that both coordinates range between 0 and 1. And I'm going to create a very simple CPPN, which has these two inputs, x and y, and one output down here, which I'll call V for the value. And I'm going to just add one synapse to the CPPN, which connects x with the output. I'm now going to enter this plane, and I'm going to visit, I'm going to just discretize this plane a little bit. I'm going to visit each pixel in this plane, and I'm going to take the coordinate of that pixel and feed it as input to my CPPN over here. Let's start with coordinate 0, 0 over here. If I take 0, 0 and feed it into my network, we don't know what's going to happen because we need a synaptic weight, so let's set our synaptic weight to 1. What happens if I feed in coordinate 0, 0? What's the value that arrives at the output? Let's assume there's no thresholding function. Let's keep this simple. 0. Okay, so the value that is placed in here is 0. What happens if I visit x equals 0, y equals 0.1? And 0 all the way up the line. What happens if I feed in as input to my CPPN x equals 0.1 and y equals 0? We get 0.1 down here, and basically we're getting the x values in here. What about x equals 0.1, y equals 0.1? 0.1, right? Okay, pretty straightforward. All right, so to save me the effort of writing in all of these numbers, I'm going to color in with the chalk. The more chalk, the closer this value is to 1. So let's get rid of my values here. Okay, so there's nothing in here, but as I move to the right, we get values that are closer and closer and closer to 1. So we get a gradient across this two-dimensional space by this CPPN. So one way of thinking of CPPNs is that they paint patterns into a space. In our case, this is a two-dimensional space. It doesn't have to be 2 dimensions, as we'll see in a moment. Let's do a little bit more drawing. Let's create a different CPPN. What pattern does this CPPN paint in this two-dimensional space? Just take it and move it, right? It would, I'll save myself some, well, let's actually draw it here, right? You could trade the x to the y. It would get darker as we moved higher up the image, right? Okay, so now maybe this cartoon makes a little bit more sense to you. Actually, let's do one more. Let's do one more. How about this CPPN? Yep.
It'll get dark towards the top right corner.
There'll be a gradient that starts white and becomes increasingly black as we move up and to the right. Yeah. Okay. Let me pause on this cartoon for a moment. There's a website which is great to play around with. This is pickbreeder.org. This was originally created when NEAT was created as a way to visualize what it's actually doing. You can see here we've got 15 panels. What do you think lies behind each of these 15 panels? What's that? A coordinate system. What lies behind the coordinate system?
The HTML button.
Yes?
Oh, a neural network?
A neural network. There's one of these compositional pattern producing networks, right, behind this. Okay, this one looks, actually this one you should probably be able to figure out, right? This one probably just has the X input layer, X input neuron connected to the output with maybe a negative weight, right? This is the opposite gradient. You can see there's slightly more different patterns. Which of these 15 patterns do you like the best? Give me a row and a column. Column 5, row 2. This one? Okay. Very exciting. And of course, because this was written in Java a long time ago, this may not work. Let's see. All this build up and it's not going to work. Fingers crossed. No? Okay. Well, you can see on the left here, if you keep going for long enough, you can actually produce some pretty interesting patterns. Okay. I'll leave it to you to go and play with this offline. Let's talk a little bit more about CPPNs. You'll notice that in this little cartoon of a CPPN over here, we have 1, 2, 3, 4, 5, 6 hidden neurons. And inside each one is a little graph. What do you think the graph represents inside the neuron? We haven't actually talked about this yet. What's that? The position function, not quite. The activation function, right? Remember that when we are computing the new value at a given neuron, we take the value of the incoming neuron multiplied by the strength of the weight plus the value of the incoming neuron times the strength of its connecting synapse. We take that raw sum and we push it through an activation function. In your case, that activation function is tan h. None of these is tan h here. Imagine inside this little picture here, this horizontal axis is the value of the raw sum. So x is the raw sum, and y is the value that is passed out of the neuron. In normal neural networks, every neuron has the same activation function. In your case, tan h, tan h, tan h, and so on. In CPPNs, which are evolved using NEAT, remember that we have back down inside NEAT, the genome specifies 2 lists that describes a network. This list describes the set of synapses. This one describes the set of nodes or neurons. There is actually in HyperNeat an additional parameter here, which is which activation function is used. And there's a lot of them. There's tan h, there's sine, there's cosine. This is not quite sine, but something similar. There is the identity function. That's the absolute value. So take the raw sum and output. Actually, it's not the absolute. It's minus absolute, something like that. Gaussian functions, all sorts of things. Why include these additional activation functions? Well, we can see why by coming back to our cartoon here. Let's make our CPPN a little more complicated. Let's add a hidden neuron here. And let's put the sine function inside here. And let's imagine now, just for fun, I'm going to change my axes here from 0 to 100 now instead of 0 to 1. What pattern is going to be produced? Actually, let's simplify this. Let's connect just the X neuron, the X input neuron, to our sine hidden neuron, and from there out to the value. What kind of pattern are we going to get inside of here now? Dark than light, right? So we know we're not using y, so we can basically just march from x equals 0 along to x equals 100. X equals 0 times 1 is 0. The sine of 0 is 0 times 0 times 1 is 0. We've got a 0 in here. So basically what's going to happen in here, as you say, is we're going to get an oscillation over time, and that oscillation pattern is going to be produced in every row of this column, or in every row of this matrix. Okay, so again, why do this? Why introduce this ability to produce these regular, often repeating patterns? The reason why is that HyperNeat was actually based on development, the way that organisms develop over their lifetime. When a single cell starts to divide and starts to produce an embryo, if you look inside that developing embryo, you start to see regular patterns being repeated over space. There is a very obvious regular pattern in our body plan. What is it? We're not just some random collection of cells. There's repeated patterns and regularities. What is one very obvious regular pattern, a repeated pattern? Heartbeat is a repeated pattern over time. But let's think about the physical layout of our body. So we've got a little cartoon here of an insect.
So like the position of our arms on our body?
The position of our arms on our body, getting closer. Arms plural, right? There's a repeated pattern.
Cells
Cells are repeated, yeah.
that were like relatively the same on either side of our body.
Symmetry, right? So when we develop from a single cell, again, it's not just this random increase in cells. The cells, as they divide and grow, produce regular and sometimes repeating patterns like bilateral symmetry. Whatever is developing on this side of the body also develops on this side of the body. If you look at insects, they're made up of a one-dimensional line of segments. Sometimes there's 3, sometimes there's 4. One of the things that development does is find interesting modules. Remember we talked about modules last time. And repeats them. It might be symmetric, it might be repeated patterns. There are some aspects of us that are only produced once. So we should also, if we want to create an algorithm that is sort of biased towards producing these regular patterns, we also want to make sure that it can also produce specific patterns. So HyperNeat is designed to evolve neural networks that don't just paint random patterns in space, right? We don't have just white noise over here. When we create CPPNs, they tend to produce regular patterns and symmetries and so on, very much like development. So the idea of this little cartoon here is to show that, for example, if we had a CPPN that was feeding the x value into a Gaussian function, it would tend to produce things on the left that are the same as things on the right. But we might also, in the same CPPN, have the Y input neuron connect to a hidden neuron that has a sine pattern, like we saw over here, which produces oscillations or repetitions along the vertical axis. And again, I apologize that I can't run PickBreeder for you. You would start to see these regular patterns emerging as these images evolve over time. So we've created HyperNeat, or HyperNeat was created to try and produce bias evolution towards painting regular patterns in two-dimensional space. The reason why is because, again, we're going to use them in a moment to evolve robots, and we would like robots to not be just some random collection of objects and joints and sensors and motors and neurons and synapses. Like natural organisms, we would like evolution to focus most of her efforts on producing robots that have regular patterns and symmetries and so on. Okay, before we switch to the next section, I've already said this now. So HyperNeat paints regular patterns onto, in this case, a two-dimensional figure, but can also paint patterns in higher dimensional space, like inside of a hypercube. So let's think about this for a moment. Let's say instead of painting patterns onto pixels in a two-dimensional space, we have a three-dimensional space, and we want HyperNeat to paint patterns onto voxels, or three-dimensional pixels inside a cube. How would we need to change our CPPN to get it to do that?
Probably add like a z dimension to that.
Absolutely. Right? We add an additional input neuron called Z, right? And now evolution can wire Z up into the CPPN, and now we will get regular patterns inside a three-dimensional space. You're going to see that we're going to do that in a moment. Might not be obvious yet why. Let's imagine that, as you can imagine, PicBreeder was designed to allow people to evolve interesting pictures. Let's imagine we wanted to alter CPPNs now to paint not just a picture, but a two-dimensional animation, a picture that changes over time. So now we're still at 3 dimensions, but we want to have an animation. How would we change? Let's go back to our CPPN that paints regular patterns inside a single image. How would we alter a CPPN to evolve animations rather than just a picture?
Can you just display it while you're iterating over each step of like it being evolved?
We could, so we could just watch we could watch the population of CPPNs as they paint images, and if we show them fast enough, it will look like an animation. But let's imagine what we're trying to do is produce one CPPN which produces an entire animation. We could have multiple outputs. We'll come back to that in a moment, actually.
You change the weight over time?
We could do that, so we could pass in the x and y coordinate of every pixel, paint one picture, save that picture, go back, change the weights, paint another picture, save that, and keep going. Yes, we could actually produce an animation in that way. It's not quite what I'm after because it's not quite the same CPPN. We're changing the weights. So for the first 0th frame of the animation, we feed in 0, and then we iterate over every pixel in frame 0, paint our picture, save that picture, put in t equals 0. We're now going to paint the second frame, go through the second frame and paint our picture, save that out, and keep going. Right? We're now painting, again, we're painting a regular pattern in 3 dimensions. 2 of the dimensions are space, and 1 of the dimensions is time. Right? So one of the things that's become so HyperNeat is now used in a lot of different domains because you can evolve regular patterns in arbitrary dimensional space and also things that change over time. Let's come back to the point about multiple outputs. Let's imagine that instead of painting a grayscale pattern, I want to paint a colored picture. How would I change my CPPN now? Kind of already given you the answer, right?
Did you have 3 more nodes for RGB?
Absolutely. So now, instead of adding input nodes, I'm going to have 3 output nodes, R, G, and B. And every time I visit a pixel, I now get 3 values back, and I'm going to treat those 3 output values as the red, green, and blue content of the color of that pixel. So, yep.
So how do you separate one output into 3 parts?
Oh, I'm sorry. I just added 3 output neurons to my network, and then NEAT, which is evolving the neural networks, decides how these neurons are attached to these neurons down here, right? If, for example, evolution comes up with a CPPN that connects to the red and the green, but never connects to the blue, then whatever you're going to have over here is always going to be blobs of reds and greens, but no blue, right? It just chooses not to use the third output neuron. Just because I supply the output neurons doesn't mean evolution is going to make use of them. So far, so good? Okay. Okay, so hopefully now the intuition is clear. We're evolving neural networks, and depending on the input, the number of input neurons and the number of output neurons, we can paint regular patterns in space and time. The author of HyperNeat, the author of NEAT is Ken Stanley. He also authored HyperNeat. This is a paper by one of his colleagues, Jeff Clune. Ken Stanley, a few years ago, went off and started a startup company using HyperNeat. This company was bought last month by Uber as their AI company, right? Every Silicon Valley company now has to buy an AI company. Uber bought Professor Stanley's HyperNeat company. Why would Uber be interested in something like HyperNeat?
Pattern recognition for self-driving cars.
That's a good guess. That's not it. Deep networks are good for pattern recognition in images. HyperNeat is not quite the same thing. Why is Uber interested in HyperNeat? Why did they pay an exceedingly large sum to acquire HyperNeat?
Because it'll be more expensive to sell in the future.
Because it'll be more expensive to sell in the future? Why? Why would companies like Uber be interested in HyperNeat? If you were the CEO of Uber, aside from public relations problems at the moment, what technical problems are you trying to solve? So for those of you who used Uber, what happens when you use Uber on your phone?
Yeah, maybe to suit a better driver to a passenger.
Possibly, maybe. Let's assume we're not worried about the social science part of Uber, technical part. Any ideas? So if you ever used Uber on your phone, what do you do?
Is it to design the route?
To design the route, right? So you have a city. There are K Uber cars at certain locations in two-dimensional space in that city. There is also the requester. There is a phone somewhere in two-dimensional space and time that has just made a request for a lift. Which car do you send to that location, right? It's all about routes in time, right? Maybe it's not just the Uber cars, it's other cars. There may be one car that's closer to the requester, but there's more traffic between that closer car and a further car. Uber is trying to solve some very, very difficult logistical problems that basically exist in a two-dimensional space over time. HyperNeat can paint regular routes in space and time. That's at least the plan. We'll see how well this works out. Okay. So it's a good thing you're taking this course. If you get an idea for a new evolutionary algorithm, the next Uber may someday buy you out. Okay. Unfortunately, in this course, we're focused just on robotics, so let's come back to robots. We want to try and use this nice property of HyperNeat now to create regular patterns in our robots. At the moment, you have your 4x8 matrix, which contains 32 floating point values, but there's no real pattern among those 32 weights, right? It's kind of arbitrary. And now that you've implemented the quadruped, you've probably seen the result of that. The quadruped tends to flail all over the place, right? There's no real regular pattern in space across the synaptic weights, which results in no regular pattern over time in the way that the robot moves its four legs. Okay. Here's a neural network. This neural network is now going to control a robot. It's going to control this quadrupedal robot here. And I'll walk you through this neural network. Let's forget about HyperNeat for a moment. Let's just go back to evolutionary robotics. We have our input layer here. These are all sensor neurons. We have hidden neurons in this middle layer. And at the back, we have our output layer. And in the output layer are output neurons. And every output neuron dictates the next desired angle that is sent to that motor. Okay, let's start with the rows here. We can see that each row in this neural network corresponds to one of the 4 legs in the quadruped. Let's go to the output layer for a moment. You can see that each leg has 3 motor neurons. The reason why is because each leg in this quadruped has 2 hinge joints at the shoulder to allow this, and 1 at the elbow. So we've got 4 legs. Each leg has 3 motors, which gives us a 4 by 3 output layer. So we've got a total of 12 output neurons. So far, so good? Okay. Each leg has a proprioceptive sensor, which returns the forward or backward angle of the hip. It also has a proprioceptive sensor that reports the in or out angle of the hip. It has a third proprioceptive sensor, which is the angle of the knee. And then finally, it has a 4th touch sensor in the foot of each of the 4 legs. So each leg has a forward and back proprioceptive sensor, in and out proprioceptive sensor, a knee proprioceptive sensor, and a touch sensor. What are these 3 reporting? They're reporting yaw, pitch, and roll, right? So it's reporting the overall orientation of the robot. So pitch is forward and backward. Roll is how much it's rolling to its left or right. And yaw is how much it's twisting about the vertical axis. So at every time step, this robot is going to receive these 3 numbers that tell it how it's changing its orientation in space. What's this one? We've seen this kind of neuron before. It's projecting a regular sign pattern into the neural network. Where did we see this before, and what was that neuron called when we saw it before?
Pattern generator.
The central pattern generator, right? We saw that when we saw the passive dynamic walker, the hybrid dynamic walker that was evolving to walk with as little actuation as possible, right? Central pattern generators they emit this regular pattern, which is useful for locomotion because locomotion requires a regular pattern over time. Right? Okay, so we have a total of 4 times 5. We have 20 sensors overall in this robot. These 20 sensors are being wired up to this hidden layer, and the hidden layer is also wired up to itself. So every hidden neuron is connected to every other hidden neuron. And finally, and every hidden neuron projects a synapse out to the 12 motors, right? Okay, why is this drawn in 3 dimensions rather than the way we've normally seen it, which is 2 dimensions, sensor neurons, hidden neurons, output neurons?
Just to visually understand it.
It helps to visually understand what's going on here. There's another reason why it's drawn in 3 dimensions.
Do they use hyperneat to symmetrically give the quadruped the same weights and synapses?
Very close. They're going to paint weights onto the synapses in this 3-dimensional space. So we're now going to make a jump. Before we were just looking at hyperneat, which is painting grayscale or color into, or in Uber's case, painting routes onto a city map. Right? We're going to go from painting those kinds of things into a space into painting now not colors but synaptic weights. Right? So we have all our neurons here, but we don't know how these neurons should be connected to each other. If we connected every sensor neuron to every hidden neuron to every other hidden neuron, including itself, and every hidden neuron to every motor neuron, how many synapses do we have? I don't know about you, I can't do it in my head, but it's a lot. Much more than 32, right? Probably we're talking about several hundred synapses. That's a lot of synaptic weights for evolution to evolve. So instead, evolution is going to evolve a much smaller neural network, a CPPN. That smaller neural network is going to paint synaptic weights onto a much larger neural network. So this experiment that we're talking about now can be a little bit confusing because we have evolution. Evolution is evolving a population of neural networks. Each one of those neural networks is then painting or constructing another neural network, and that neural network is controlling the robot. We're now talking about a pretty complex algorithm, but there's a good justification for doing this. If I just ask you to build this quadruped in PyroSim and evolve those several hundred synaptic weights, 5 years from now, your laptop would probably still be going, right? We need to try and reduce the dimensionality of this problem for evolution. It's going to work in this lower dimensional search space with these much simpler networks. And these simpler networks are going to produce gradients of synaptic weights throughout this three-dimensional space, not unlike the way that CPPNs paint regular patterns of paint onto our pixels in two-dimensional space or three-dimensional space. So far, so good? You understand why we're introduced this extra step? Okay. So next question we got to ask is, if we want HyperNeat to paint synaptic weights into this network, what's the input layer, right, for our CPPNs? We could, for example, create 3 input neurons, X, Y, and Z. We could then create every synapse. Let's take the synapse that connects this neuron to this neuron. So we've got this synapse here. Let's take the midpoint of that synapse, which exists in three-dimensional space. Remember, this network is sitting in three-dimensional space. Take the midpoint of that synapse, which gives us an XYZ, pass that into a CPPN. It produces a single output, now W. We have a single output W, which is the weight of that synapse. Now we connect this neuron to this neuron. We've got this synapse. We take this X, Y, and Z coordinate, pass it into the same CPPN, but because it has a different X, Y, and Z, it gives us back a different W for that synapse. And we paint those several hundred synapses using this CPPN. We could do that. There's a bit of a problem with that. A little tricky to see. Anybody see what it is? I mentioned that we have this hidden layer here. Imagine that every hidden neuron has a recurrent connection that connects to itself, and every hidden neuron is connected to every other hidden neuron. We're going to put some recurrent connections in here. It's a pretty strong hint.
A lot of the recurrent connections would have the same midpoint and they would have the same weight.
Exactly. So let's just take 2 neurons here. Let's just do it in two-dimensional space. We've got, I'm not sure if you guys can see. I'll put it over here. Let's say we've got these 2 neurons here. We have one synapse that connects this neuron to this neuron, and we have a second synapse that connects this neuron to this neuron. We need weights for both of these synapses. What are those weights going to be, regardless of what the CPPN is? Or tell me about these 2 synaptic weights. They're going to have to be identical, right? The midpoint of these 2 synapses is exactly the same. So from the CPPN's point of view, it's going to output exactly the same value. Perhaps we would like these 2 synapses to have different weights, right? So in order to do that, they introduced one more wrinkle to this algorithm, which is, as I won't draw this now, you can see that the input to the CPPN now has 6 coordinates, x1, y1, z1, x2, y2, z2. What do you think those 6 coordinates represent?
One direction and the other direction.
Not quite. No, this is the input. Remember that we're always inputting the coordinates of a single synapse. We're trying to paint just one synapse at a time.
The coordinates of the two neurons the synapse is connecting.
Exactly. So this represents, if we have a synapse that connects neuron 1 to neuron 2, this is the coordinate of neuron 1 and the coordinate of neuron 2. So now if we're trying to paint this synapse, we feed into our CPPN the x, y, and z coordinate of this neuron and the x, y, and z coordinate of this neuron. If we're then trying to paint, for example, if there were a synapse going back the other way, we would just reverse the two three-dimensional coordinates, and we might get, depending on the CPPN, different values. And again, we still have a single output. Okay, let's try and put all this together now. We have a population of neural networks, CPPNs. Those neural networks are being evolved by NEAT. NEAT allows evolution to change the structure of these CPPNs. What is the fitness of any given CPPN? Well, we take that CPPN, we get it to paint the synaptic weights onto this neural network. We then take that neural network, drop it into our virtual robot in PyroSim, let the robot do its thing, and we get back from PyroSim a single number, the fitness of that robot, and we assign that fitness back to the CPPN in our population of evolving CPPNs, and rinse and repeat and rinse and repeat. So far, so good? Okay. If you're very ambitious, you can try and implement this. I assure you this is a pretty tricky one to get right, but very powerful if you do. Last thing I want to say about this before I show you some results. Notice that we now have a neural network which exists in 3 dimensions, but HyperNeat is painting patterns into a 6-dimensional hypercube. The CPPN doesn't know anything about this lower dimensional neural network. All it knows is it's painting, as far as it knows, it's painting colors or it's painting something in the inside of a 6-dimensional hypercube. Luckily for us, we don't have to try and visualize that picture. We could just look at the synaptic weights. Unfortunately, I don't have time to go into this, but if you Google HyperNeat, I think on Google Images, you'll see some nice pictures of neural networks in 3 dimensions, and then they just colorized the synaptic weights, so you can actually see regular patterns of synaptic weights throughout an artificial neural network, which is embedded in 3 space. You can definitely see that there are regular patterns. If you were to draw your 2-dimensional neural network that connects 4 sensors to 8 motors, and you turn the synaptic weights into colors, you wouldn't see any pattern, right? It would just be completely random. Okay, so after all that, I think I've said all this already for you. Yeah, okay. So after all that, this algorithm better do some useful work for us. How are we going to know whether it did useful work? Well, we're going to compare HyperNeat, the algorithm I just described to you, to a similar algorithm, but it's missing one piece, which is we're going to take out HyperNeat. We're going to call this competing algorithm FTNeat, for fixed topology neat. This is going to use the same neural network, and by neural network they mean this neural network. So in this competing algorithm, we're just going to evolve the several hundred synaptic weights for this network in exactly the same way you're doing it in the assignments. Okay. And sorry, they're allowing for mutation and crossover, but not the addition, removal of neurons and synapses. Sorry, I misspoke. So they're evolving these networks directly, but they're using NEAT to do it. So NEAT can add and remove synapses from here, but it cannot add and remove neurons. It's just fixed with what we give it. So far, so good? Okay. Thankfully, HyperNeat definitely does useful work for us. So they did multiple evolutionary runs. For every evolutionary run, they let it run for 1,000 generations. And they then looked at how far the robots traveled in the physics engine. over evolutionary time. And we can see in the case of hyperneat, in most of the evolutionary runs, after 1,000 generations, the robots were traveling 6.5 units into the screen. With FT-neat, the robots were moving more than twice as slowly. Okay, let's see if I can show you some videos here. Okay. This is FT-neat. So this is the fixed topology neat, the competing one. This was the best one they got. Best one they were ever able to achieve. Tell me about this gate. We're back to Monty Python's Ministry of Silly Walks, right? You can tell that already the motors are a little bit too strong, right? But other than that. Is it producing regular motion over time? Not quite, right? There's short periods here where 3 or 4 of the legs are moving together, but not really. You can kind of tell that that's what evolution is trying to do, right? It's trying to find a set of synaptic weights that gets the legs to move in a coordinated fashion, but is definitely not able to do it. Let's see if I can find the other one for you. Okay. Okay, so now this is the best gate that was produced using hyperneat, where they were using CPPNs to paint regular patterns across the neural network. This one's not slowed down. Kind of loses it at the end there, right? Not perfect, but pretty close. It can be done. You can actually sort of work backwards from the way the legs are moving to sort of think about how this CPPN painted weights inside this robot's neural network. Any ideas? So if you watch carefully, see if we can take a frame here. These 3 legs are moving almost identically, right? So however it's painting the weights are probably similarly projecting onto those 3 legs. There is probably a repeated pattern. Remember, this is what hyperneat is good at. There's probably a regular pattern of weights, or the same pattern of weights that are being projected onto the back right, back left, and front left leg. And then a version of that pattern, which is painted onto the front right leg, but it's somehow inverted. There's probably a negative sign in there somewhere, because those 3 legs all move in phase together. The right front leg moves in the same way, but in perfect antiphase. So not a 4-legged gait you tend to see in nature, but works perfectly fine, right? Okay, so now we've seen this is probably the most complex algorithm we're going to see in this course. And there's good reason for doing this, right? We're evolving controllers for our robots, but we're using an algorithm that was developed to be, that was created to be a model of development. Because development in nature produces organisms that also have regular patterns over space, bilateral symmetry, and also regular patterns over time, our heartbeat, for example, or our steps during walking. We now have an algorithm that biases search towards these regular patterns in space in the neural network, which, at least in this experiment, we can see also translates into regular motion over time in a legged robot. Okay, it's a couple more slides, but I think we'll leave those for next time. You have a quiz due tonight. You're working on assignment 9, and I will see you next Tuesday. Thank you.